Hello and namaste everyone. Welcome to this class on the NPTEL course on stochastic approximation. This week, as I told you last time, we are going to recap some of the important concepts and some of the important ideas that we have discussed or maybe we have missed. So I am going to recap some of them, right? And in the previous class we looked at some important concepts from probability. In this class we are going to look at some important concepts from real analysis and also look at some ideas from single time scale stochastic approximation and two time scale stochastic approximation. With this in place, let us begin our formal discussion, right. So here is some statement from real analysis. So you could be asked some question in this along these lines, right. So the statement goes as follows: let Kn be a non-increasing sequence of compact sets of Rd or compact subsets of Rd, and the question asks, can we say whether the intersection of these Kn sets, whether it is compact or not. That is what is being asked. Furthermore, we have been asked, if this intersection is empty, can we conclude that the Kns themselves become empty for all sufficiently large n. So let us see how we could go about proving this result, right. So first let us try to show whether this intersection Kn is compact or not. Now recall the definition of compactness. A subset of Rd is compact if and only if it is closed and bounded, right. So since each Kn is compact, one can conclude that Kn is closed for each n, and since we are taking in countable intersections of closed sets, we can conclude that intersection of Kn is also closed, right. Furthermore, we know that intersection of Kn is a subset of Km for any m, and we know that Km is bounded, which means that every element in Km, right, has some bound on has some finite bound on the norm, on its norm, and hence one can conclude that since intersection Kn is less than Km, this intersection must also be bounded, and hence one can conclude that intersection of Kn is both closed and bounded, from which we can conclude that intersection Kn must also be compact, right. So next we will prove the second statement, which requires us to show that if this intersection is empty, then Kn is empty for all sufficiently large n, right. So towards this we will make use of what is known as proof by contradiction, right. So what is the proof by contradiction? We will suppose that the conclusion that we need to show is false and somehow show that that will lead to some contradiction with regards to the setting of the problem. So towards that, suppose your Kn is not empty for every n, right. So here we need to show that Kn is empty for all sufficiently large n. So here we are presuming that, look, however large n you pick, your Kn is not empty, right. So suppose Kn is not empty for all n, right, and because it is not empty, right, one can conclude that there exists from xn in Kn for all n in capital N, right. So actually the contradictory statement we are presuming also makes use of the fact that your Kns are non increasing, right. So here we have been told that it is a non increasing sequence, which implies that your Kn is it is non increasing, right. So it means that Kn must be bigger than Kn plus 1. So this fact and this fact that we have been given that for all sufficiently large n, Kn is not empty, right. So together we can show that Kn must not be empty for all n in capital N, which is the set of integers, right. So since Kn is not empty for all n in the set of integers or the set of natural numbers, one can conclude that there exists some element, let us call it as xn, that belongs to Kn for all little n in the set of integers, right. And because we have this non increasing nature, which means that Kn is a superset of Kn plus 1, one can conclude that if you look at the tail of this sequence of xn's, in particular if you look at xm for all m bigger than equal to n, it must be the case that xm belongs to kn, right. So n here is fixed and we are only changing m. So for every m bigger than n, it must be the case that xm belongs to kn. So in other words, if you start from some point on, right, with regards to this sequence, then all those elements will belong to the same set, right. In particular, since if we look at k1, one can conclude that xn belongs to k1 for all n, and since k1 is compact, in other words in particular it is closed, one can conclude that xn must have a convergent subsequence. So let me repeat again, right. K1 is basically the topmost set, right. So you have something like k1 here and let's say something like this, and k2 is basically a subset of this, k3 is a subset of this, and so on, right. And since we have presumed that your kns are non-empty, right, and which implies xn belongs to kn, and because of this non-increasing nature, one can conclude that all those all elements of the sequence must belong to k1. And since k1 is compact, in particular it is closed, one can conclude that every sequence, right, has a convergence subsequence, and whatever be its limit, that limit also belongs to this set k1, right. Whatever be the limit, its that limit will belong to k1, right. Now my claim is that because you have this convergent subsequence, and the limit of a convergent subsequence doesn't change if you only look at the tail. So what do I mean by that? So let's say you have a sequence xn, and here we are presuming that this sequence has a convergent subsequence, and let's say this is your convergent subsequence, and let me denote this as yk, right. So yk is basically x subscript nk, right. Now if I only look at the tail of this yn sequence, that is yn, or I should perhaps use yk, okay. So let's say if I only look at the tail of this sequence, by that I mean if I look at yk for k bigger than m, right. So if this sequence converges, then this the tail of the sequence will also converge, right, and if this converges to x star, then this must also converge to x star, right. And we know that the tail of a sequence, right, if you sort of sufficiently go far away, will belong to km for any m, right, and hence one can conclude that because each of these sets are compact, right, and in particular closed, which implies that the limit must belong to that set, one can conclude that this x star belongs to kn for all little n in capital N. So in other words, what we have managed to show is that there is one element which belongs to every kn. In other words, the same x star belongs to kn for all n in capital N, and hence one can conclude that this intersection is actually non-empty. In particular, it has this element x star, right. So since x star belongs over here, this is non-empty, but this contradicts what we have been given. So recall the statement. So the statement said that if this is empty, but we managed to show that if this holds, right, or the opposite of this statement holds, then your intersection must be non-empty, and hence that leads to a contradiction which tells us that for all sufficiently large n, your kn must indeed be empty. Okay. Alright, so this sort of gave us some insight of these compact sets and so on and so forth. So this property is actually used in multiple proofs in stochastic approximation textbook written by Professor Vivek Borkar. You can actually go over that textbook and figure where this is actually used. Now let's move on to some other concept that we have studied or looked at in this class, which is that of I shouldn't say this class, I should say in this course, which is that of ordinary differential equations, right. So here is one question related to ordinary differential equations, a very simple and basic question. So the question says, suppose you have been given an ODE of this form, that is x dot of t equals -2 times x of t, and the question asks, if we are given the initial condition x of 0 equals 5, then what is the value of the solution trajectory of this ODE with this initial condition at t equals 2, right. So I should perhaps say what is the value of x of t at t equals 2, right. So the easiest way for such a problem would be to find explicitly the solution to this ODE, and which is what we are going to do. So what this ODE tells us is that dx by dt, okay, so this thing is basically dx by dt is equal to minus 2 of 2 times x of t. So if you sort of take this x of t to here and dt over here, this differential equation basically tells us that I mean this differential equation from the fundamental law of calculus tells us that we can integrate this quantity, and whatever solution we get as part of that will actually satisfy this differential equation. So let us take this relation over here and integrate it from t naught to t, which will tell us that the integral of dx of t x of t from t naught to t is equal to t naught to t minus 2 dt, right, and the integral of this is basically log x of t, and the limits are from t naught to t, and here the integral is 2t and the limits are t naught to t, hence we will end up with t minus t naught. So if you make this substitution, one can see that log of x of t by x of t naught will equal minus 2 times t minus t naught, from which we can conclude that x of t must be x of t naught times e raised to minus 2 of t minus t naught, right. And we have now been told that x of 0 is 5. So if I substitute or replace t naught with 0, one can see that x of t will equal 5 times e to the power minus 2t, right. So one can see that as t becomes larger and larger, this quantity decays, in particular as t goes to infinity, this thing goes to 0. But what we have been asked is what is the value of x of t for t equals 2, and one can easily see that by substituting t equals 2 here, that it is equal to 5 e raised to, sorry I made a mistake, this is indeed if I substitute t equals 2, it is e raised to minus 4 times 5, right. So x of 2 will equal this quantity over here. Is this okay? So please be aware or see how you can develop strategies to solve ordinary differential equations, okay, because that play a very important role in what is referred to as the ODE method for convergence analysis of stochastic approximation. The ODE method is very powerful because on one hand it tells us what could be the potential limits of a particular stochastic approximation algorithm, and on the other hand any ODE can also be a potential source of an algorithm, right, that could be useful for the application that is of interest to you. So ordinary differential equation helps us in both ways. In other words, if you had an algorithm, then the ODE method could help you predict what could be the potential asymptotic behaviors of that algorithm, and vice versa. If you have an ODE which in some sense shows some interesting behaviors, then you can use that ODE and identify a stochastic approximation algorithm whose limiting ODE is the ODE of interest. So in that sense ODE actually plays a very important role in the study and design of stochastic approximation algorithms. So a good understanding of ODE theory consequently will go a long way in your study and applications of stochastic approximation theory. Okay, so now let us move on to the other part of this course, which was that on stochastic approximation. So in stochastic approximation we looked at various forms of stochastic approximation algorithms. In particular we looked at stochastic single time scale stochastic approximation, then we looked at 2 time scale stochastic approximation, and then we looked at some set valued generalization of stochastic approximation which we referred to as stochastic recursive inclusions. So in this class I will give a very quick recap of some basic stochastic approximation algorithms and also some 2 time scale stochastic approximation algorithms. So here is a very basic single time scale stochastic approximation algorithm, and what this algorithm says is that suppose you have a sequence of iterates xn which are generated via the following update rule, that is xn plus 1 equals xn plus some step size, which in this case is 1 over n plus 1, this is multiplied by yn plus 1 minus xn, where your yns are independent and identically distributed random variables and all have the same expected value 2, right. And the question asks us, can we say something about whether this sequence of iterates converge or not, right. And if it converges, let's also look at can we somehow say something about the potential limit, right. So this is one of the very basic stochastic approximation algorithms. In fact, this is a stochastic gradient descent algorithm. I mean, I encourage you to figure out why this is a stochastic gradient descent algorithm, right. So let's use our ODE method to figure out what can we say about the limiting behavior of this algorithm. So towards that, what we first do is, let us define delta n to be whatever is there in the square bracket, which is yn plus 1 minus xn, and then what we will do is we will identify a sigma field such that this xn is measurable with respect to this sigma field. However, yn plus 1, right, is not measurable with respect to this sigma field, right. So one such sigma field is basically the sigma field that is generated by the random variables x0, which is the initial value, along with y1 to yn. So notice that in the update rule for xn to xn plus 1, right, you have yn plus 1 over here and not yn. So we actually take x0 to and y1 to yn and use those random variables to define a sigma field, and we will refer to that as fn, right. And then one can easily see that xn, okay, which is the nth term of your stochastic approximation iterates, one can see that xn belongs to fn, right, where fn is this sigma field. And when I say belongs to, I mean that xn is measurable with respect to fn. In other words, I mean, one easy way to figure this out is, if I give you the values of x0, y1 until yn, can you tell me what will be the value of xn, right. So one can see that indeed by using this formula recursively and knowing the value of x0, y1 to yn, one can indeed precisely identify what is the value of xn, and hence one can conclude that xn is measurable with respect to fn, right. So because xn is measurable with respect to fn, if you take the conditional expectation of delta n with respect to this sigma field, and since delta n is yn plus 1 minus xn, and since xn is measurable with respect to fn, the conditional expectation of this will leave xn unchanged. However, the conditional expectation of yn plus 1 given fn, and now making use of the fact that your yns are all independent and identically distributed, in particular your yn plus 1 is independent of the past, and hence the conditional expectation of yn plus 1 given fn will basically be the expectation of yn plus 1, and since these random variables are all identical, we will refer to expectation of yn plus 1 as expectation of y, and we have been told that this quantity is 2, hence this is basically 2 minus xn. Is this okay? Alright. So hence what we can do is, we can rewrite the given update rule in the following way, which is xn plus 1 equals xn plus whatever step size we had, and whatever is the conditional expectation of delta n given fn, we will write it over here, but we can't just write something because that will change it. So we will subtract that as well, and by subtracting it we will get hold of mn plus 1. In particular, your mn plus 1 is basically whatever we had before, which we referred to as delta n, right, and whatever additional quantity we have added, right. So we subtract it over here, hence this difference is what we will refer to as mn plus 1, right, and here one can see that these xn's will actually cancel off, and we would actually end up with yn plus 1 minus expected value of y, right. And one can trivially see that if I take the conditional expectation of mn plus 1 by fn, right, the way we have designed or defined mn plus 1, it will trivially hold that this conditional expectation is actually 0 for any n bigger than equal to 0, and hence one can conclude that this sequence mn is actually a martingale difference sequence with respect to your sigma field fn, right. So this is just the way we have defined these quantities. One can trivially see that your mn will actually turn out to be a martingale difference sequence, right. So the nice thing about writing it this way is that if we can verify some of these assumptions that we had stated when we sort of went over chapter 2 and chapter 3 of this textbook called as Stochastic Approximation by Professor Vivek Borkar, one can see that one can easily identify the limiting ODE that sort of captures the asymptotic behavior generated by these iterates, right. In particular, if you define h of x to be expected value of y minus x, right, then one can trivially see that h of x is Lipschitz continuous. In particular, it is linear and hence it is Lipschitz continuous, and one can verify the other assumptions of stochastic approximation as well, which is that your step sizes satisfy these Robbins-Monroe condition, right. That will be satisfied because we will choose our step size sequence to satisfy those conditions, right. And furthermore, your martingale difference will satisfy this linear growth condition that can be very easily shown to hold over here again, right. And finally, one can look at the scaled ODE and use that to conclude that your xn's will actually be almost surely bounded. Now, since all these conditions hold, one can conclude that xn will actually converge to an asymptotically stable equilibrium, or I should say asymptotically so perhaps I should say maybe this is not the right thing. I should say that it will converge to a closed connected, right, internally chain transitive invariant set of this ODE that is mentioned over here, right. However, this ODE has the property that because of this negative sign over here, it has the property that expected value of y is the unique globally asymptotically stable equilibrium point, right. So that is the only invariant set that I shouldn't say only, it's the only compact invariant set that this ODE has. Of course, the whole real line will be invariant, but it won't be compact. But we know from the theory of stochastic approximation that if certain assumptions hold true, then xn will converge to a suitable compact invariant set of this limiting ODE, and we know that the only compact invariant set is this unique globally asymptotically stable equilibrium point, which is expected value of y, and since that is the only invariant set possible for this ODE, the theory of stochastic approximation helps us conclude that the iterates of our stochastic approximation algorithm will almost surely converge to expected value of y, right. And since we have been also told that expected value of y will be 2, we can now conclude that if you make use of this algorithm that is specified over here, then indeed these xn's converge, and in fact almost surely they will converge to this specific value 2. Okay. So at least you should be able to do such simple analysis of where a stochastic approximation algorithm can potentially converge to, right. So now we come to the last part of this class and also the last part of this course. So I will sort of give an overview of 2-time scale generic 2-time scale stochastic approximation. In this class we actually discussed I shouldn't say in this class, in this course, when I actually discussed 2-time scale stochastic approximation, I looked at this very specific example of solving a linear system of equations in the presence of adversaries, right. So there, if you remember, I estimated expected value of y on one time scale and used that to solve the linear system of equations on another time scale. But if you look at this textbook on stochastic approximation by Professor Vivek Borkar, you will see that the generic form of a 2-time scale stochastic approximation is what is given over here, right. So here your xn will have the update rule that is given over here, and yn has the update rule that is given over here. So let's go over this carefully. So xn plus 1 equals xn plus some step size plus some update rule of the following form. In particular, xn's driving function is h of xn comma yn, and there could be some noise over here, and yn's driving function is g of xn yn with some different noise. So here I have written mn plus 1 1 and mn plus 1 2 to indicate that they are two different noise components. But the key thing to observe here is that I am using a different step size to update your yn iterate, and I am using a different step size to update your xn iterate, right. Now if xn and beta n, sorry I should say if alpha n and beta n, if they are of the same order, which means that let us say alpha n over beta n, either they are always constant or maybe alpha n over beta n converges to a constant. So let us say xn alpha n over beta n either is equal to c, or alpha n over beta n goes to some constant c which is strictly bigger than 0 and is less than infinity. So if such a condition holds, we will say that even though you have written it this way, your xn and yn are actually updated along the same using the same step size sequence or the step size sequence of the same order, in which case we will still view this as a single time scale stochastic approximation. On the other hand, let us say alpha n and beta n have the property that either alpha n over beta n goes to 0 or alpha n over beta n goes to infinity, which basically implies your beta n over alpha n goes to 0. In that case we will say that these two iterates actually refer to a 2 time scale stochastic approximation. So of course we also require that alpha n and beta n themselves satisfy the standard Robbins-Monroe condition, which is that your summation alpha n should be infinity, similarly summation beta n should be infinity. On the other hand, summation alpha n square and summation beta n square both should be less than infinity. Right, now let us see why this condition sort of becomes necessary, right, and what are the implications of this condition, right. So let's suppose this condition holds, then what we can do is we can rewrite xn's update rule in the following way, that is xn plus 1 is xn plus beta n, right, times this expression, that is whatever you have over here, right, and we multiply each term by alpha n by beta n, so that whatever we have over here matches what we have over here, and we keep yn's update as before. Right, now you can see that the same step size appears over here and here. Hence if you define Zn to be the combination of x and yn, then we can write this two update rules jointly as follows, that is Zn plus 1 equals Zn plus beta n times capital H of Zn plus mn plus 1 plus epsilon n, where this capital H of Zn, okay, will basically be made up of 0 and g of x and yn. Your Zn will basically be made up of x and yn, right, and mn plus 1 will be made up of alpha n over beta n, mn plus 1 1 and mn plus 1 2. So I have basically tried writing whatever you saw previously in a joint fashion, right, and finally one can see that epsilon n will have this form, that is it will be made up of two components. The first component will be alpha n over beta n times h of x and yn, and the second component will be 0, right, and one can see that if somehow we manage to show that the iterates are bounded, then h of x and yn will be bounded, and since alpha n over beta n goes to 0, then epsilon n will go to 0 as well. So in other words, your Zn plus 1 equals Zn plus beta n times this expression where this quantity somehow goes to 0. So if you only focus on this part, one can immediately conclude that the limiting behavior or the of these Zns will then be dictated by this limiting ODE, which is that x dot of t equals 0 because you have a 0 over here, and y dot of t equals g x of t y of t. Now notice that here x dot of t is 0, which means that wherever you start the x of t trajectory, it will remain there from that point of time. What this means is that from the yn step size perspective, your xn looks static, right. So what it means is that from yn step size perspective, which is beta n, right, the update rule for xn looks like it is not moving xn at all, right. So because of this reason, from yn step size perspective, xn doesn't look to be changing. Because of that reason, what we will say is that from yn step size perspective, xn is the slow update, whereas yn is the fast update. Now let me try to relate it to these algorithms where you actually run nested for loops, right. So what do I mean by nested for loops? You have an outer for loop and you have an inner for loop. So for one iteration of the outer for loop, you could run multiple iterations of the inner for loop. So when you run the inner for loop, you may be doing some calculations, and whatever is the output of that inner for loop, you use that to update some variable of the outer for loop, and in the next iteration of the outer for loop, right, that whatever variable you had computed in the previous iteration, that will be in some sense kept fixed, right, and then you run some additional calculations using your inner for loop. So in some sense a 2 time scale algorithm represents that, right. So here you can see that the x value is fixed because x dot of t is 0, whereas you are only updating y of t where the x of t value is fixed and y of t value changes according to this dynamics over here. So because of this reason, from yn step size perspective, xn is referred to as the slow update and yn's update is referred to, or the yn iterate is referred to as the fast update, right. So in some sense this gives you an overview of how 2 time scale stochastic approximation behave, and in particular they mirror in some sense the behavior of nested for loops. Okay, so this brings us to the end of this class and also this course. I hope you had some interesting insights from this course, and in case you enjoyed this course and it helps you with your applications, do let me know. I'd be happy to listen to it and give my own feedback. So while I have tried my best, I noticed that there were a couple of mistakes that appeared during this course. If you find one explicitly, do let me know. I'll try to at least address them as part of the comments. So I hope you enjoyed this course. Until we meet next time, goodbye, namaste, and thank you.